Welcome to video 9.1 in our first Principles of Astrophotography series. In this video we discuss image degradation due to atmospheric turbulence called seeing.
Speaking of seeing, I had a cross-eyed girlfriend once. It didn't work out.
Oh, I'm sorry to hear about that.
We couldn't see eye to eye, and I'm pretty sure she was seeing someone on the side.
Oh, that's nasty. This video is based on section 9.1 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. Principle 115, seeing. The term seeing describes image degradation due to atmospheric turbulence.
It's at the atmosphere. That's where it is. That's where it's happening.
Yeah.
That's what we're talking about
Right.
here. Yeah, so we have plane waves from a distant point source. So think about a star, galaxy, whatever. Those waves are coming in, they're nice and smooth. These are the wave fronts or wave crests. They're coming in, then they hit the turbulence in our atmosphere, then they get perturbed. And they get messed up, bottom line. So a couple of examples of this. On the upper right is a jet as seen through the exhaust fumes of another jet. So those exhaust fumes are extremely hot. They're mixing with the cold air. And that causes lensing effects because the index of refraction of air depends on its temperature. The hotter the temperature of the air, the less dense it is, and the lower its index of refraction, the closer it is to 1.
Isn't it more the temperature differential, though?
Yeah.
There has to be a temperature difference. Not just...
if it was all a uniform temperature, you wouldn't see these effects.
Right. Yeah.
It's the fact that we got hot air mixing with cold air, and that causes the problem. Same kind of thing happens on a road. You've got a hot road or a hot sand in a desert. The refractive index near the hot road in that hot layer of air is lower than the refractive index outside, so it acts like little lenses as that mixes with the colder air above, and you see a kind of a shimmering effect. You can also see this in the sky. You can see when you look at stars in the sky, they twinkle, and the reason for that is atmospheric turbulence. And you might say, well, that twinkling isn't a very big deal, but if you're magnified by 100 times or whatever, then you're just magnifying all of those imperfections as you magnify. So it is a big deal, and it's important to take into account, and that's what we're talking about in this section.
Balance. Principle 116, seeing resolution. The seeing resolution is characterized by the full width at half max of measured intensity profiles of unsaturated stars.
So in our book we talk about seeing resolution for visual observing, and that's a different set of rules. For visual observing, you're trying to wait for moments of good seeing. You're looking through an eyepiece, you're looking at Jupiter, for example, and it looks like a fuzzy blob, and then suddenly it snaps into clear focus, and then it gets fuzzy again, and then it wobbles a little bit, and then you can see a couple of cloud bands. The visual observers have their own way of characterizing how much of the tremors and these things are happening, and they characterize the seeing by the extent of those tremors. But in astrophotography, especially in long exposure astrophotography, where you're taking 1-minute exposures or 5-minute exposures, all those tremors and undulations and oscillations get averaged out, and you just end up with, instead of an image that's jumping around, you just end up with a blob. And so the way that long exposure astrophotography measures resolution, how much resolution you can see in the sky, is to just simply say, let me look at the full width at half max of star intensity profiles. So if you look at the intensity as a function of angle, and this is the center of a star profile, and this is the intensity as a function of angle on the sky measured from the center of the star profile, then the full width at half max, here's the max, here's half the max, and this distance here, like we talked about in a previous video for area profiles, is called the full width at half max of the measured intensity profile. So as we talk about in the book, and I think we talk about it in a future video also, these profiles for long exposure photography, because of the seeing effects that are going on, they're much wider than you would see for the airy profile. They're just a whole lot wider. And that airy profile is getting moved around, and that's just life. It's just what we deal with now. Ren has it in with, and you know, he's in with Elon Musk, and so he's going to work out a deal where he can go up on one of Musk's spacecrafts and look at the sky through a spacecraft.
Yeah, definitely. That was sarcasm.
Yeah.
Yeah.
So, or if you have a close relative that works for the Hubble Space Telescope, you can go up and take your telescope in there. I don't know, but for the rest of us humans here on the Earth, we have to deal with the atmosphere.
It's hard being immortal.
It's tough. It's really tough. So Attila Danko, and I'm not sure I'm pronouncing that name right. I've only seen it in print. But he came up with these clear sky charts, which are widely used in the industry to characterize cloud cover, transparency, and seeing. And this is the category that we're talking about right here. Those clear sky charts are based on weather predictions, so that's where they get the cloud cover predictions. And also, the seeing predictions are based on a model by Alan Rahill of the Canadian Meteorological Society, or Center. And what he's come up with is a model of what the seeing is going to look like based on the atmospheric conditions. And the model characterizes the seeing by the full width at half max, and basically he's saying that if that full width at half max is greater than 4 arc seconds, then that's pretty no bueno seeing. That's
not good.
That's no fun. Between 2 and 4 in this chart is considered to be poor, and between 1 and 2 is average, and between 1.4 and 0.9 is good, and less than 0.4 arc seconds, so the stars are really, really small. You'd actually have to have a telescope that's big enough to actually, that has an area profile that would allow you to do that. I think in Mauna Kea, we talk about this in the book, the observatory on top of, in Hawaii, they get, their average seeing is 0.43 arc seconds.
It's pretty good.
So,
well, that's pretty low as far as elevation goes too, right?
no, it's up there. I think it's at 13,000 feet. It's on top of
okay.
Mauna Kea. It's way up on this mountain, and
I think Hawaii. I think coast.
yeah. Now I think we'd have to look it up, but it's it's on a mountain, and I think one of the reasons they get good seeing is that, according to what I've read, there's a steady sea breeze that's always blowing. It's a continuous, very steady, not jiggling a lot.
Yeah.
And so you get this. So associated with each of these categories of seeing is a color in the clear sky charts. And you'll also see these colors in Astrospheric, which we use all the time and highly recommend. It's a astronomy weather prediction app that shows the clear sky chart information and the predictions by Alan Rahill. And so the dark blue, so if we're looking at the seeing color, this I believe is the medium blue color, which corresponds to a day of average seeing.
Yeah.
And this looks like maybe the light blue, not sure if that gray, either poor or really, really bad, but I just did a screenshot of this. But if you're getting this dark blue color, then in the seeing category here, then you're talking about a good night.
Great.
And it's a good to go. So that's how seeing is characterized for for long exposure astrophotography. Now for lucky imaging that we talk about also later in the book, this seeing does not apply. And the reason, and I think we talked about it in a previous video too, is that you're taking extremely short exposures, maybe 75 exposures per second, and you're freezing the seeing. So you're not getting all this jiggling. You're capturing one moment of the jiggling, and then with the miracle of the software, you're taking all these images that are showing Jupiter in different places and stretched in one and compressed in another and out of focus in another. They put those together and get the detail that you see. And we have one photo in our book, not by ourselves, that's absolutely spectacular of Jupiter. It just looks like a Hubble photo. So that's seeing resolution. Thanks so much for watching.
And we'll see you next time.